now.
Hi, this is Mike Masterson. I'm an automation specialist with the Reynolds Company, and we will be talking today about Parallel Redundant Protocol as part of our Resilient Network series. Assisting me today is David Newt. He will be my co-presenter. And also online, we have Brandon Singh and Mark McGinnis online to help us with any questions we might get. Okay, we've got some upcoming events we want to talk about. On Thursday, June 18th, we have our users group, which will be on ControlLogix Redundancy. On Wednesday, June 17th, we will be doing industrial networking, our industrial networking series, Tech Talk, and we will be covering the Converged Plantwide Ethernet architectures. Then on Tuesday, June 23rd, we'll be revisiting SIP security in our control systems. And with that, we'll get started and talking about Parallel Redundancy Protocol. Our agenda today, we're going to do a quick overview of it. Then we're going to be taking a look at topologies, PRP and the CPWE architecture, which is the Converged Plantwide Ethernet architecture that Rockwell promotes with Cisco. And then we're going to take a look at general considerations for the network, what we need to be aware of when we start trying to utilize Parallel Redundancy Protocol. Now, first thing I want to make everyone aware of, we do have good documentation on this network. What you see in front of you is the design and implementation guide for Parallel Redundancy, which is a subcatalog of our CPWE manual, which we'll be addressing in our Wednesday's podcast. This guide has a lot of information on how to use it and configure the network. And just to let you know, there are 2 additional documents we have access to. And those would be the Parallel Redundancy Protocol Application Technique, the Distributed Control System User Manual, and the Stratix Managed Switch User Manual all have information on Parallel Redundancy and how to set it up in the switch. Now with that, we'll get over with the general overview of Parallel Redundancy Protocol. Where we're going to start on this is what is a redundant network to begin with. Can you pause? PRP is a truly redundant protocol, while a lot of our ring environments are more of a resilient protocol. Remember, any ring type topology we do is actually a linear network, where they're actually using blocking to create the linear network. That cuts down from the traffic storms. What parallel redundancy is doing, we're running 2 side-by-side LANs that mirror each other exactly, going back to the controller. So they are truly, truly independent and truly redundant pathways. Ultimately, what is happening is we are sending the data out of 2 ports, and whoever gets to the end device first is the winner. The other data is thrown out. So that's what separates it from a true ring. It's a true redundant pathways. Now, why would you want to use parallel redundancy for everything? Well, for one thing, it's very expensive and it's very hardware intensive. You have to use a lot of switches. Quite often, a resilient network such as a ring, you can get almost the same type of uptime status with it, but it's much simpler and less expensive to implement. So that's why you have to take a look at your what you're trying to accomplish and pick the right network for your application. Okay, Parallel Redundancy Protocol is a standard. It is not a Rockwell protocol per se, but it is an IEC standard. You can find Parallel Redundancy Protocol supported in many manufacturer switches. Usually the higher end ones you will find out. It is supported by ODVA. It's truly a redundant, fault-tolerant layer 2 design, and more importantly, it is a sorry, David, I'm kind of. So ultimately, Parallel Redundancy Protocol is an open standard and is used by other networking companies also. The components of the Parallel Redundancy Protocol, obviously, this is something Rockwell likes to use, so acronyms will come into play. So to bring you up to speed, these are some of the things that we will see in a parallel redundant protocol network. The double attached node, that would be like the 1756 EN2P or the Flex 5000. These are comms adapters that can take the two separate networks that we're using parallel redundancy into a, let's say, like an IO chassis. The single attached node, this is a device that does not support parallel redundancy protocol natively. This is something like an engineering workstation or an HMI terminal, which we don't need to put on both networks because it's not really doing a lot of the control. It's just there for visualization or something like that. So we don't have to go to the expense of putting, making special arrangements to put it into a parallel redundant network. And we have the RedBox or the redundancy box. This is a device we use to put devices that don't support PRP natively onto the network. The RedBox is in our case, it's a Stratix 5400 switch that has the capability of being an interface for PRP directly. That gives us the ability to take our virtual, that gives us the ability to put devices that don't support redundant or PRP natively onto the PRP network. As this gets more and more confusing, there's also the virtual DAN. This is a device that does not have PRP technology that connects both LAN A and B. Basically, a VDAN is what is attaching to the RedBox. Now, obviously, we have our LANs A and B segments, and then the infrastructure switches, which do not have to support PRP natively. If you're just going to switch to switch format. Now, on the communications layers, what exactly is PRP? Well, if we take a look at the stack, the first thing you should notice is that we are not doing anything up top to the stack. All the data is going there the same way. The IP address and MAC address will always be the same. Basically, all the switching is done below in the lower areas. Now, one important thing is because PRP does add a trailer to their data frame, we do want to use, to be a PRP switch, you do need to be able to support jumbo frames or the larger frames. Some switches cannot do that, so that's very important. And that's why our Stratix 5400 has that capability to handle the larger frame sizes. Now, as far as the RedBox operations, you'll take a look at the Strax 5400, which is our DIN rail mounted switch, can handle one PRP channel, which would be our 2 different networks. And our 5410 can have up to 2 networks, PRP networks on it. Maximum number of 500 virtual double attached nodes. Again, VLANs are devices that are attached to the RedBox switch. And the switch will send the supervisor frames to the VLANs. And obviously, like I said earlier, if the first data that gets there is accepted, the other frame will be thrown out. And with that, I'm going to bring in my counterpart, David Newt, and we're going to start talking about topology examples.
All right, thanks, Mike. And special thanks for everybody tuning in today to learn more about Parallel Redundancy Protocol. So the rest of the discussion, the tech talk, I'm going to show a lot of topology, some use cases, and really a lot of graphical representations of the Parallel Redundancy Protocol network, which is really kind of a good way to kind of sort of get a better idea of what you can do with Parallel Redundancy Protocol, or PRP. And so the first slide here is kind of a basic topology slide to really put a location from all the devices that Mike had just talked about earlier. So here you can see the ControlLogix chassis are the dually attached nodes, or the DANs. So you have a controller and an IO chassis that are connected via LAN A and LAN B, dually connected directly. So hence the DAN, or the DAN.
And David, those controllers would have to have the N2TP cards in them for the communications, correct, if they're acting as a DAN?
That's correct. A good point, Mike. Thank you for that. And also up to the left side, you can see the redundancy box for the RedBox, which is how we connect other devices that don't natively support PRP to both LAN A and LAN B simultaneously. Hence, you see the VDANs on the left-hand side. And then on the right, you see an HMI that's the singly attached node. And so that's your SAN. That's, in this case, just attached to LAN B. So a couple of things that we want to make sure we understand here before we go forward. First of all, inside LAN A and LAN B here, we just see clouds. And so we're going to go in and define a lot of different architectures or potential architectures, what you can do, and also some things about what you cannot do in a PRP network. But inside those LAN A and LAN Bs, those switches need to be managed switches. And one of the reasons for that is because we have 2 independent networks that communicate independently, the application doesn't recognize any faults that would happen. So the network infrastructure needs to be able to recognize its own faults. And so that's why we recommend using managed switches inside the LAN A and LAN B infrastructure. And also, it's important to understand that the best practices for building any kind of network are still in place here with a PRP. There's nothing magic about PRP. So all your best practices for physical media, network design, and security would still apply in a PRP network. So first, let's take a look at a couple of use cases. So what we're looking at here is a parallel path network. And so you've got 2 independent paths going from a ControlLogix redundancy system down to the IO. And in this use case, you could be looking, physically different parallel paths, like something like a tunnel or like a ship or something, where you can easily set up independent paths that are separate from one another. And this is certainly a good example of a somewhat simple use case with PRP. And then one step further, if you did have a parallel path network, you can easily, inside LAN A, LAN B, you can add things like ring protocols, and that could be a rep ring, a DLR ring, etc. So with not a whole lot of extra cost or not a whole lot of extra work, you could add some resiliency inside your LAN A and LAN B networks. That is something that's certainly allowed in the PRP structure. Another use case example, and one that we see fairly often in the process industries, would be a dual ring topology. And so what you see here would be at each location, each IO location, and at the ControlLogix Redundancy location, you have two sets of switches, and those switches are independent rings that are that communicate over PRP. And also, you do have the ability to add a red box to the ring if you wanted to connect things like drives or HMIs or anything else that is not directly
critical
PRP compliant. And you may, even before Ethernet, we've been using dual rings for a lot in the process industry. So those of you that have done ControlNet redundancy in the past would recognize an architecture somewhat like this. But some of the advantages here is that this is an Ethernet network, so so you have a lot more options than just the dual ring, hence the red boxes and other things. And so another use case or another topology application example would be a star or a redundant star. And so in this example, with the same number of switches in a dual ring, you could also construct would be like a redundant star you see here. And so in some physical applications, it may make more sense physically to build a redundant star, or in other cases, a dual ring may make more sense. But because this is an Ethernet technology, you can do either topology would work. Okay, so the next few slides, we're going to talk about some invalid topologies or things that you really cannot do or highly recommended that you do not do in a PRP system. And when you're designing a network, it's very important to understand what you cannot do and sort of build a framework and a boundary around what you cannot do, so you end up with a full functional high performing network. So the first thing that's a no-no is you cannot connect the LAN A and LAN B in any way. And because Mike mentioned earlier, the PRP sends out identical communication stacks from the MAC address up to the application layer. That communication stack needs to be independent. And so anytime you mix those two, you're going to have issues. So whether it's a direct connection or a industrial switch in between the two LAN A or LAN Bs, or if it's a controller you're trying to bridge or an ETAP or something, it's just something that you do not do. You'll end up with broadcast storms and some serious network performance issues. So
yeah, the basic takeaway from this, you cannot, the only things that can attach to both LAN A and LAN B are a red box or a double attached node. Those are the only things that can fit between the LAN A and LAN B switches.
Yeah, thanks, Mike. So here's another invalid topology. So here we have LAN A, LAN B that is separate until we get to the red box. So you can have a vast number of red boxes on a PRP network, but the two red boxes cannot be connected to one another. A red box by definition is already connected to LAN A and LAN B, so they do not need to be connected to each other. And again, this would also cause potentially some broadcast storms and would also have other performance issues that we want to stay away from. So red boxes are connected independently, or red boxes are not connected to one another. They're connected to LAN A and LAN B directly. And some other examples of unsupported topologies would be LAN A and the LANs connected between themselves inside LAN A and LAN B through something like a bridged Ethernet module in a Logix chassis or an ETAP. And so these part of one of the main reasons for this is Mike also mentioned earlier, PRP communicates using the larger communication packets that ETAPs and network bridging just don't handle well. So, but the industrial Ethernet or the Ethernet switches, the 5700s, 5400s do handle those better. So that's why we recommend using fully managed switches and not the smaller things like ETAPs or ControlLogix chassis. Another thing that can create problems is when LAN A and LAN B are dissimilar networks. So you never want to combine a low latency and a high latency LAN together. And because inherently with the way that PRP works is you have the two identical packets that are sent two different ways. And so if you have a significant time difference between one and the other, then you potentially have switchover issues and communication issues. And so you just want to stay away from it. It's not to say you cannot have Wi-Fi or satellite connections in a PRP network, but the two networks just need to be very similar so they have similar performance latencies.
Yeah, and that's very similar to when you ran dual ring control net, because that had the same thing. The pathways had to be similar in length, because if they were skewed too much, you would start having packet errors with control net also. So this is something we have seen before in networks.
That's a good point. And so finally we have, or not quite finally, but moving on from what you can't do or some recommendations is NIC Teaming. So those of you that don't know, NIC Teaming is typically technology came out of the server environment, and it allows you to connect to build a team of network cards or NICs in a server. You can also do it in a workstation that allows for internally within the operating system to have failover and increased resiliency inside the communication. So NIC Teaming is supported, but we support it through connecting through a RedBox. And so there's a couple of illustrations here on the basics of how to set up if your server or if your workstation is doing some NIC Teaming. The idea is to connect it to a RedBox first, and then allow the RedBox to handle the LAN A and LAN B communication. You don't want to connect a NIC Teaming device directly to LAN A or LAN B. Without going into a lot of details, the main reason for this is you present yourself with a lot of convergence issues on the NIC Teaming device if there were a failover. And so we just like to separate the NIC Teaming directly from a PRP through a RedBox. So moving on slightly, we're going to introduce PRP as a part of the larger Converged Plantwide Ethernet network architecture. And so for those of you that aren't aware, the CPWE is a methodology design recommendations that have been created with a partnership between Rockwell, Cisco, and Panduit. And so there's quite a bit of documentation of techniques and designs and application recommendations on how to build a fully plant-wide network. And so that's not the scope of this discussion. But what is the scope is how do you apply a parallel redundancy protocol architecture to the larger plant-wide Ethernet structure. And so this example shows you really what the correct way would be to connect this to a PRP to a CWE system. And so the way you do that is you connect your, in this example here is a dual ring for simplicity, but you would connect the PRP directly to a set of distribution switches. And those the distribution switches in a CPWE are typically layer 3, and they're typically implemented in a redundant fashion. So you have an HSRP, which stands for Hot Standby Router Protocol. So you have an active and a standby distribution switch, and both of those, and so you have that. But most critically are those distribution switches need to be red boxes or redundancy boxes. And so essentially you're connecting the larger plant network to the PRP via red boxes. And so the Rockwell Stratix distribution switches are all redbox compliant. Cisco makes redbox compliant switches, and there are also some third-party distribution switches available that have this functionality, that are layer 3 and support HSRP and are red boxes. So that's basically how you do it. And there's other ways to implementations, and for that you can check out the CPWE and PRP manual that Rockwell's published. But it is important before we move on to explore a little bit how the data flows inside a CPWE network and how it differs from the PRP. And so, as we've discussed up to this point, the PRP network sends identical packets. And if you have a failure, or if you have an issue, there's a zero convergence time, which means there is no issue with, there is no downtime on the network. And so, although the CPWE has resiliency built all throughout its architectures, there is, even with redundant switches and things, there is some convergence time that's associated with a CPWE network. And so to understand that, you need any devices that you really need to be connected on the network with a zero convergence time need to be inside the PRP cloud or inside the PRP architecture. And then so outside of that architecture, you could have things like maybe your data centers or your HMI controls, or I'm sorry, your HMI system or some of your data systems, which could survive. And what I'm talking about here is at most 3 seconds or so of a convergence time. So your control and IO can't survive that. So they need to reside inside of your PRP network and other things like drives and stuff. In this example, kind of goes into some detail about how the traffic flows. So instead of, so it goes through the distribution active switch, goes up to the core switch, and then down back through the distribution switch, and depending on which one's active is the one that where the data flows through. So moving on, we're going to talk about some other network services and protocols and how they work with PRP. So the first service we'll talk about is VLAN segmentation. And so I think this is a really good slide. This slide gives you an idea, number one, of probably a popular, what will become a popular PRP architecture, the dual ring inside your control and IO. It's also connected here to the larger CPWE network through your distribution switches. And inside of the PRP, we may have a process network that we want a VLAN, and then we may have a safety network on the right-hand side. Look at VLAN 20 with a safety controller talking to drives. You may want to create a VLAN here, and this is kind of how you would do it. And so again, for more details around how this is set up and configured, you can refer to the CPWE manuals. Multicast is supported. So Multicast is a technology that we use quite a bit in ControlLogix Redundancy, and also controller-to-controller communications. And so this is an example of how a PRP network could use multicast. Really, the thing to keep in mind here is on a multicast network, the distribution switches need to be the IGMP querier in the network, and so your industrial or your infrastructure switches, you just need to turn the IGMP querier off and allow the distribution switches to handle that communication. That's really the takeaway here.
And all that's covered in the CPWE guide that we made reference to in the beginning of this topic.
Yeah. And so we'll talk just for a minute about ControlLogix redundancy with PRP, specifically related to the controllers. And so using the EN2TP module, which was the initial PRP compliant module available in the ControlLogix platform. Using those modules, now you can, not only do you support PRP, but there's also two different configurations or you can run in them. So you can either enable or disable IP swapping. And so that's important because as you're segmenting your network between your IO and your HMI, those two networks have different needs. So the IO network or the SIP class 1 data needs to support the IP swapping, so you can have a seamless transfer between, if you did have a swap over between controllers. However, the HMI data really doesn't need that functionality because the HMI data just needs to get data flow. Doesn't need that exact or precise class.
It's not as high a priority, basically.
Yeah. So in the HMI data, if you turn off IP swapping, that really what that does is that reduces your the convergent time potentially in your HMI on a swap over, and so that functionality is available with the version 31.052 of the firmware, and also with Factory Talk Links version 6.11 or later. There's a new shortcut. There's a redundant primary secondary controller shortcut that's available in the Factory Talk Links. And another thing about Factory Talk Links is beginning, I believe, with version 32 of Studio 5000. It's becoming, Factory Talk Links is now becoming the kind of the default communications that we're using now on the controllers. You can still revert back to RS Links Classic, but from version 32 on, the default communications is now using Factory Talk Links. So that's something you'll see a lot more of going down the road. Okay, so another question you may be thinking of is how do I connect my PRP network or my PRP network to a device level ring network that may already be existing. And so the quick answer is yes, you can do that. There's different ways to do that. And this system here would be part of a larger Converged Plantwide Ethernet system. So if you notice there on your ControlLogix redundancy there at the bottom, you've got an EN2TP Ethernet module, and that's connecting to your PRP network. And then in order to connect that ControlLogix redundancy to your other DLR gateway, the proper technique would be to add an additional network module that supports DLR, maybe an EN2TR, that connects directly to that DLR network. And so therefore that's one way of having two completely separate networks on your ControlLogix redundancy system. And so this is how you do it.
And actually, there's actually 3 networks there because they're also using Ether channel off the DLR network to their access switch. So they're using port aggregation as that connection, which is a little bit different than the DLR and the PRP.
There you go. Yeah, thanks, Mike. And so here's another example of connectivity to a DLR. So we're looking at a redundant ring PRP network. And let's say the use case or the example would be you've got some existing DLR rings, and how do you connect those to, and maybe in a non-redundant situation like this. So you've got, so another way to do that would be, excuse me, through a RedBox. And so what we're looking at here is a RedBox. This would be a 5400 Stratix, because this RedBox is, or this switch is actually supporting 2 separate DLR rings. So you got ring 1 and ring 2 there. And then through the RedBox functionality, it is also connecting directly to both LAN A and LAN B PRP networks. And so, you know, this is not fully redundant. So it would be a non-redundant RedBox with DLR, but there's a lot of different ways to slice networks, and this would be one way of doing it in a non-redundant fashion. So here's one thing that we do not recommend and do not support with respect to DLR, and that would be DLR redundant gateways with RedBoxes as currently not supported. And you know, the main reason for that is a setup like this, we would encounter typically high convergence times between the primary and secondary redundant gateways. And so at this time, we're not recommending this type of network. And so that's also listed in the documentation as something that we don't recommend doing. So network address translation, or NAT, is supported with PRP. And so there's a couple of use cases here on the screen. One would be directly on the LAN A and LAN B switches. So that is supported. So if you did want to use address translation on inside of LAN A and LAN B, that's supported. And also address translation is also supported on the RedBoxes. So that's it. So finally, let's talk just a little bit about precision time protocol with PRP. And so precision time protocol has been around for a while. Its use case really focuses around all the devices in a network having to be in lockstep with a timestamp. And so that a lot of times you may see that in certain
a lot of high-speed
applications or drive applications where motion critical positioning is required throughout a large system. Could be a conveyor, could be all kinds of things. So the quick answer is yes, you can communicate through a PRP network with time precision protocol, but there is a difference. And so all up to this point, we've been talking about PRP sending duplicate packets, identical packets to LAN A and LAN B. The difference here with precision time protocol is it is a network with a active and a passive path. And so within the time precision protocol, you communicate over the active path, and that doesn't change even with the PRP network. And so time precision protocol has swap overs and has resiliency built into it, and that resiliency is still maintained through the PRP architecture. And so this is an example, a little more detailed, maybe a more real world example of what a time precision protocol architecture would look like. So you have maybe one controller may have a GPS clock, and so that would be the timestamp that the whole network has to follow, and so that timestamp communication gets sent throughout the network, and so this is an idea of not only through LAN A and LAN B, but also through a RedBox. We do support the time precision protocol through a RedBox. I guess one takeaway here would be inside LAN A and LAN B, the infrastructure switches need to be set up as a transparent clock, allowing the clock communication to go through the networks, and then the RedBox switch is a boundary clock, and so there's slightly different ways that time stamp is handled through a boundary clock. And so just keep in mind that the RedBox needs to be a boundary clock in a precision time protocol network. So are there any questions today? I guess I'll wait just a second. I don't see any at the moment. So again, Mike and I really appreciate your attention today, and appreciate your sticking with us on this
acronym heavy topic.
Yeah. So we thank you for your attention, and if you do have any questions about the PRP network, please contact your local automation solutions specialist, and they'll be more than glad to help you. Thanks again, and have a great day.